have covered yesterday. Okay, now we continue with the representation of phase equilibrium data. We now move to ternary mixtures, but still one component distributing. This is a very important special case. We will go to ternary mixtures, even though you would have probably gone next to binary where both components are distributed. This is a simpler case to handle. So the classic example is when, again, ammonia, we have already seen that in the typical case of absorption of ammonia or carbon dioxide or so on using some solvent, we have it's often a good approximation that there is no water vapor in the gas phase, right? So this becomes the case of binary with one component distributed. Suppose I have a mixture of ammonia and air or some various other gases. It can be a mixture of other gases. The only requirement is that none of them dissolve in the water, in the solvent. Then it becomes an easier case to handle than the full ternary mixture. So again, we look at the variables. It would be temperature, pressure, and then I have y energy and x energy. We now have two variables. What is the degree of freedom? Degree of freedom is now, maybe we have, I can consider air as one component. And in fact, it would be a mixture. Typically in industrial absorption, ammonia comes with a mixture of various other gases, or let's say carbon dioxide, along with various other flue gases and so on. So all of those, obviously our choice of the solvent would also be, better solvent is one with which we absorb only the ammonia or carbon dioxide which we want to be removed from the gases. The rest of the thing we choose a solvent so that they are relatively insoluble. Now we are considering an extreme case where they are pretty much insoluble. So the degree of freedom is 3 now, meaning air as one component, minus 2 plus 2 is equal to again 3, and not 3 actually, this is now 3 as compared to 2 earlier, and we have now 4 variables, and so the only equation I have is still F. Now, Taylor makes a very interesting comment. What he says is that suppose I consider the earlier case where I just have ammonia, right? And then we could, for instance, at a given temperature, I could plot the pressure versus solubility. Because there are only 3 variables, so temperature, pressure, and at a given temperature, I can plot the pressure versus solubility. Here, at a given pressure, I can plot the temperature versus the solubility. Now, in a typical curve like this, that will make it look like this. So, what he says is that the same curve can be used here. For this case, when ammonia could be present with a mixture of various other gases, the only restriction is that none of them dissolve in water. And he says I can use them for this case also, provided the coordinate, so y-axis is converted to the partial pressure of ammonia. Again, the only problem is that you have to understand the special reason or conditions under which this is valid. This is not, cannot be valid generally. But the point here to make is that what he is effectively assuming now, what is the model that we choose? Here I have already chosen. That is not going to change because from this case, the earlier case when air is not present, right? The model for liquid is this, the Henry's law. Now, in this case also the liquid hasn't changed in character. It's still a mixture of ammonia and water. You might consider the same relation to hold good. What about this? So what Trevor says is correct, provided we treat now the gas as an ideal gas mixture. Under that assumption, what he saying is correct, that the pressure axis for the pure component can in fact be treated as the partial pressure, because after the right hand side hasn't changed. So whatever was the pressure earlier now becomes the partial pressure of ammonia. So we can use it. So the advantage of this has to be seen is that suppose I am able to generate this data using just ammonia. Right? So I don't need any other gases to unnecessarily mix it. So I can conduct whole set of experiments just using pure ammonia, absorb it in water and generate all the solubility curves. Then I can use it for any other system where ammonia could be present in a mixture of gases, provided only that those do not dissolve and sufficiently low pressure that the gas phase can be treated as an ideal gas mixture. So various other examples are also possible. For instance, in extraction, another case of ternary, there is now two liquid phases. We have not considered that. So for instance, typically when you have an organic mixture, right, let's say I have acetone and benzene in one phase, and then acetone and it's going to be lighter. But anyway, it's not physically represent literally what would happen. But what I'm considering is only a schematic. Suppose I have a mixture of acetone and water, and I want to extract the acetone out of that. So obviously I will add, one way to do it is through distillation. And then I create a vapor phase by adding energy. Another way is to add a third component, and again our choice would be such that the solvent that I am using, actually if I want to extract acetone, I have to make sure that as much as possible the other component is not extracted into the other phase. So benzene is a good solvent for this, because benzene and water are substantially insoluble in themselves, and even in the presence of acetone, that's a good approximation. So this is another case. Only here again temperature, pressure, I can say x1 first phase acetone and x2 acetone. Only one equation. So this is again a case of F is being equal to 3. Right? So F again is continuing to be 3. This is obviously one equation and 4 variables. This is another example of a single component distributing in a, but the mixture is ternary. Right? That is the important simplification that we get. Of course, the models there would be somewhat different because the liquid phases and these ideal gas type of models won't work. Let us now go to the next case, which is binary mixture where both components are distributed. As you can see, in case of ternary mixture with only one component distribution is a slightly more complicated case than the binary mixture with only one component. Essentially, it's the same. Now we go to binary mixture. Both components are distributing in, both components are present in both phases. So here I will consider a very important case of distillation, which will largely focus on calculations. So distillation, what will happen, I consider a mixture of A and B, and so I have now a vapor phase and a liquid phase, both contain A and B. Now so I can choose, so the variables are temperature, pressure, and so I have to choose one of the component mole fraction. I can choose it to be the mole fraction of A in the liquid phase and the mole fraction of A in the vapor phase. We have one independent composition variable in each phase because it's a binary mixture. The number of variables is 4, and of course the degree of freedom is C minus equal to 2. So among the 4 variables, only 2 can be independently chosen. So let's now look at the representation of phase diagram. So if typically presented as a constant pressure or constant temperature. Because if I have to plot this, two of the variables are independently varied. The other two, if I have to plot, it will be a four-dimensional plot. So typically what is done is choose a constant pressure or temperature section. Right? So if you take a constant pressure, and what is plotted? The temperature versus composition. And interestingly, the conventional to plot both the temperature versus liquid as well as the temperature versus vapor composition. So this is can be regarded as, let's say, composition will be mole fraction of A. The temperature versus liquid, let's say, will look like this, and the temperature versus typically will look like this. How do we interpret this diagram in the context of the phase loop? So these are the envelopes which separate the single phase from the two-phase region. This is T versus Y. I will explain what Y means and what X means. Y obviously means the mole fraction T versus YA. So clearly, first of all, this is composition of A. So this is clearly pure A. This is value of 1 and CV. So this would correspond to what temperature? The boiling temperature of which component? Of B, right? So this is the boiling point of B at this pressure, and this is the boiling point of A at the same pressure. We are focusing only on one pressure. And again, Ravi is a very good source for these kinds of diagrams, but here we are interested in how the phase loop works. So this would be the vapor region, or actually vapor. This would be the gas. This is the subcooled liquid. That's the superheated vapor, which can be denoting as G. So that's a single phase region. So now, since the degree of freedom for single phase, this is only for two phase. Single phase, the degree of freedom is 2 minus 1 plus 2, which is equal to 3. They have 3 degrees of freedom. So to fix the state, what it means is that I need to specify 3 of the variables. So the single phase, there's only one. So I call it temperature, pressure, and set A. Degree of freedom is 3. That is single phase we know, C plus 1, right? 2 plus 1. So pressure, I fix one variable, right? And temperature, let's say I choose this temperature because I am in the single phase. So it's still not fixed. I choose the temperature, but still, what is the state? Let me anyway, right? So I need to fix the mole fraction also. Then the state will be fixed. Similarly here, I'm calling it Z because it can be either in the gas region or in the liquid. Similarly here, in this whole region, below the T versus XA curve, right? So I need 3 variables to fix the state. Pressure is already chosen. I need 2 extra variables. So they would have to be the temperature as well as the mole fraction. Okay? So that is a single phase. We are interested more in the two phase. The two phase is where we have 4 variables. The pressure is chosen. So I have to be the two phase means I have to be between these regions, these temperatures. Right? So I can choose a temperature. Right? Let's say call this T star. That's the chosen temperature. Now, according to the phase loop, that's sufficient to fix the state of the two-phase system. So what it means is that the two phases, the composition are already given by the way we intersect the envelope. So this is will clearly give me X star A. This would give me Y star A. So this is often what is referred to as a tie line. Connects two mixtures which are in equilibrium with each other. Because if we don't know this, then I am giving you this is T versus Y, this is T versus X. The question is, I can connect and they don't have any meaning where they intersect. What we want in two phases, which are the two phases in coexistence, right? So I can draw an arbitrary line like this, it intersects at some x, it intersects at some y. They are not the ones in equilibrium, right? So that is determined by specifying the temperature must be the same for both the phases in coexistence. Otherwise, we have some liquid and some vapor, which is corresponding to some other vapor liquid equilibrium mixture. Right? So you have to know how to connect the two phases which are in coexistence. So that is given by these tie lines. So typically, so this is what is referred to as a dew point curve. So we should know all these. This is the dew point temperature, this is the bubble point temperature. The reason given often is that suppose let's say we draw it in a parallel manner here. And we plot it like this, constant pressure temperature, one fraction A. So this is the A here is referred to often as a more volatile component because its boiling temperature. I can also plot it as a fraction of B. Weight is plotted that this is the boiling temperature of A is lower than that of B. That means it's a more volatile. It means that we start boiling at a lower temperature at this pressure. And so now, suppose I have a mixture here. ZA. This is now liquid. If I start heating it at constant pressure, then it will reach this point. Its temperature will increase. So this is where the first bit of vapor is appearing. Bubbles of vapor are being formed in the liquid. So that's why it's called as a bubble. So at that point, this will be the mole fraction of the corresponding vapor. Now as I continue this at the same pressure, so you get as the process proceeds. Now this will be the state of the liquid, this will be the state of the vapor. Now the actual point here, normally from thermodynamic point of view, this line, actually this is often called as a region of two phase, but there is actually no region. From thermodynamics there is only one state here and one state there. There is nothing in between. But however, we can give a meaning to the region inside as a mixture of liquid and vapor. That mixture, this is often referred to as the overall, then it becomes the overall composition. Because I am not taking any material. This whole thing is taking place in a closed system. So the total amount of A, the total amount of B are remaining the same. Only they are distributing differently in the liquid and vapor. So when I say, but it starts from here, let's say T0, and I'm proceeding like this. So why am I drawing it on the same line? Because the overall composition of the mixture is not changed. Right? It is simply moving along the constant overall composition. So when I go here, this may be represented as the overall mixture, but strictly the only two points that have meaning are this and this from thermodynamics. There are two phases, but I can look at the two phases together as a whole system, and then you can easily verify that the overall composition, that's the total number of moles of A in the liquid and vapor put together, divided by the total number of moles of A plus B, will clearly be given by this, because I am not removing anything from the vessel. Everything is taking place in a closed vessel at a fixed pressure. So what is happening is that the same amount of A are present within the vessel, but they are distributing differently between the liquid and vapor. And you can see that the mole fraction, so when it finally reaches this point, this is called as the dew point. That will be the last bit of vapor. So this is the dew point. Not the last bit. At that point, all the mixture would have been effectively vaporized, and this can be regarded as the composition of the liquid at that point. After which it will entirely become superheated vapor, or you can call it gas. So the liquid composition will move along this envelope. The corresponding vapor compositions would move along this envelope. All this you must be familiar in your earlier courses on mass transfer and so on. So this is what happens. And now, from the point of view of mass transfer, separation becomes important. So you can also consider higher temperatures. For instance, this is higher pressures. So when you go to higher pressures, the whole curve will move up. So if you're going from let's say this is T1. Okay, we have got it here. You can also see the various. So this is let's say one pressure. What will happen at a higher pressure? It will move to higher temperatures. The whole curve T this is. So if this is at P1, all at P1, the higher curve will be at a higher temperature, and also the envelope will become, the region enclosed by envelope becomes smaller and smaller. So P2 greater than P1. So what you can clearly see is that from the point of view of separation, we are also interested in, it becomes more and more difficult to separate because the difference between the liquid and vapor phases are becoming smaller and smaller. That's what it means. The region enclosed by the envelope is shrinking. What it means is that because when we want separation, we want as much difference in composition. That's why we are creating vapor in the first place. And we have 50%, let's say, liquid A and B. So I want to vaporize it. So the vapor maybe will have 63% A, and the liquid will have less, right, of A. So that is the whole idea of separation. Separation is more and more difficult, and it says that at sufficiently high pressures, even the region of composition over which two phases will exist will become smaller and smaller. So beyond a certain composition, I have only one phase, whatever you want to call it. So you won't have liquid and vapor over the whole composition range. And this Trayvon, even Sandler refers to it as the so-called critical solution temperatures, right, and so on. We're not going to go into that. But an interesting variation. Now the whole thing can also be plotted on a constant temperature section, right? So we can plot the whole thing with constant temperature. We should be aware of this because when we do the calculation, we will see that there are 4 standard types of calculation. One is called the bubble point temperature, bubble point pressure, dew point temperature, dew point pressure. So it depends on what is being specified. And if you know, you should be able to relate your calculations to the figure. Right? So for instance, if the pressure is specified and let's say the composition is specified X, I want to calculate T, so that will become what is called as a bubble temperature and so on. We'll come to that in detail later. So if you have a constant temperature, then we plot pressure versus composition of A. Right? Now, if let's say A continues to be the more volatile component, then the pressure versus composition will have a envelope like this, will be sloping upwards, because at a given temperature, the saturation pressure of the more volatile component will be greater. Right? So you can regard it like that. This is the saturation V sat of A, and this is V sat of B. So now again liquid and vapor, higher pressures correspond to liquid phase. So clearly this is now going to be the liquid phase and this is going to be the gas phase. Liquid and vapor will be given by this. So this will be now what you can call as a bubble curve. This will be the dew point curve representing the vapor phase. So that we should be very much aware of. Because the same thing we want to be reflected here. The distinction here is, you can see the more volatile component. Another way of looking at the definition of more volatile component somewhat vague and not very precise. But here what you can see is clearly boiling point of A. That's the easiest way to remember. Boiling point of A is greater if you start heating both A and B separately and go on increasing the temperature. A is obviously going to evaporate fast, quite early. Right? That's one way of looking at it. But you can also see that it's also reflected in the fact that the vapor, while A at any temperature is greater than X state. Given, so that means the more of A in the vapor than the mole fraction of A in the vapor is more than that in the liquid. Right? That is maintained here. So you should be very careful because the pressure, this now becomes the liquid and this the vapor. So if I have any temperature and a given pressure, let's say, so where this will correspond to liquid, this would be XA and this would be YA. Same thing is maintained. YA is always greater than X. So you cannot change the character of the system by just plotting on a constant temperature section. Right? So that is maintained. But however, the whole idea of more volatile and less volatile will become somewhat nebulous when we look at systems which exhibit an azeotrope. That's also very important class of system, both from a mass transfer separation point of view and from thermodynamic point of view also. So that can be plotted like this. I've got a constant pressure. Maybe tomorrow I can show some graphs here available in the standard textbooks. Now the temperature versus composition, let's say, of A, and again the dew point and the bubble point. Now you can clearly see that here both the T versus X and T versus Y are monotonically decreasing. Now in the case of an azeotrope, what you will get is, let me first plot the T versus Y. You undergo, let's say, either a minimum or a maximum. Based on that, we characterize azeotrope as a minimum boiling. This is again with about terminology you should be very clear. Minimum boiling means we are saying that the T versus composition will undergo a minimum at fixed pressure. And it's possible to show that if you choose, for instance, to plot it on a constant temperature, it will actually show a maximum, the pressure versus composition in the same region of temperature and pressure. You will see why that is the case. Now the dew point, the bubble point will look something like this. So now let us see what happens. So this may not both be the same. So you just so now you have to understand that this is continues to be T versus, maybe I can do this slightly different color because here the character of the, so this one changes, so I want to distinguish. So this red is now the dew point curve. This is T versus Y and this is T versus X. So now let us see what happens. At the azeotrope, you see what happens. Now let's look at the composition of the, let's call this Z azeotrope. That's the composition corresponding to the azeotrope. Why it is called an azeotrope, I don't know. But now you look at compositions to the left of the azeotrope. That means compositions lower than that of the azeotrope. I take a liquid here, right, and heat it. Whatever your experience there, exactly the same thing will happen. In the sense that at any temperature, the YA will be clearly greater than XA. Now, but however, to the right of the azeotropic composition, so you take any liquid which has a composition greater composition, a mole fraction of A greater than the azeotropic composition, and then do the heating process, you can clearly see this is now the vapor. At any temperature, actually XA will be greater than YB. Obviously, these two XA and Y are not the same as those two. But if you want, I can call it, let's say T1, we'll call it T2, what happens is the nature changes. So you can regard now which is more volatile from the point of view of pure components. You can still regard A as more volatile, definitely less, even the metal appears almost as if they are the same. So just imagine that continuous E, void point of B continues to be more than that of A, let's say. But however, this character which we associated with the more volatile component, that its mole fraction, the vapor phase will be more than that in the liquid phase, that does not remain constant throughout that feature is not maintained throughout the composition range. And to the right of the azeotropic composition, it will actually be inverted, right? And so the vapor in a sense becomes richer in B than in A. Right? So you cannot say which is more volatile and which is less volatile very clearly. Now at the azeotrope itself, what happens is that you start from a liquid at the azeotropic composition, right? Then there is no range over which liquid and vapor coexist. This is one important characteristic of mixtures over pure component. Because we have seen that the pure component saturation coexistence curve is a single curve. So at every temperature there is only one saturation pressure. And at every pressure there is only one temperature over which liquid and vapor will coexist. But here you can see for the mixture, there is no single boiling temperature, the fixed pressure. The mixture effectively, when you regard boiling as representing liquid and vapor in coexistence, right? So you can have a whole range of temperatures over which liquid and vapor will coexist. So this range will change as you change the composition. Now the azeotrope is somewhat often connected to like a single component, because here it will be, it is a liquid all at this temperature, the temperature, azeotropic temperature, the azeotrope. At that point, it will actually be a mixture of liquid and vapor at both the same composition. So there are no two compositions. Y azeotrope is equal to X azeotrope. That's what is happening. So what will happen when you take a liquid at the azeotropic composition and heat it, right up till the azeotropic temperature will become a liquid, right? After that, it will become a vapor. So what happens at the azeotropic temperature will be coexistence. You might not see it very clearly because their X and A are both the same. So I cannot plot it differently, right? So it will be a mixture, two-phase coexistence at the azeotropic temperature, where XA is equal to YA, and then it will entirely become vapor. So this is somewhat like a pure component boiling, right? So we can also have, this is what is called as a minimum boiling. Minimum boiling means at a fixed pressure the temperature will versus composition curve will undergo minimum. And maximum, so the very famous example is like ethanol, water. At around 90 mole % ethanol, we have a minimum boiling at 1 atmospheric pressure. And Weber also points out that by sufficiently lowering the pressure, we might even be able to get rid of it, because azeotrope, as you might all know, it places a limit on the maximum. So this is ethanol 89% peak. The ethanol is roughly more volatile, so you hope to get it in the distillate. But in a typical distillation column, you cannot get more than 89% or 90% purity in the distillate. So that places a limit, fundamental restriction on the maximum separation that can be obtained in a single distillation column. Right? So there are many methods of overcoming this. Right? But what Traeger also points out that by sufficiently lowering the pressure, we might be able to eliminate the azeotrope altogether. So that's one way of vacuum distillation and so on, low pressure distillation will help, might help, we don't know, I don't know about ethanol, what a meant azeotrope actually will completely disappear. He points out, gives a number of examples, and I think one of the examples he used for a maximum boiling azeotrope, very famous example, is HCl water. Now the azeotrope has attracted a lot of attention because of confusion regarding the interpretation of the phase rule. Now if you see, there are 2 degrees of freedom for a two-phase system, right? And typical statements of the phase rule say I can choose any 2 variables, and then the state is automatically fixed. But you have to be very careful because azeotrope, such a literal strict interpretation will not hold. I will explain why. Now suppose you say 2 degrees of freedom are there, I have chosen the pressure. 1 degree of freedom is exhausted. Now let us say I choose a particular temperature, let's take T1 itself. So I am now given P is equal to P1, P equal to T1. Now is X A and Y A, are they uniquely determined? Are they not uniquely determined? Is it a unique? Is the state fixed? It's not fixed because I have one XA1, YA1, another, right? P2 is above, another which I will call as XA1 prime, or maybe there's YA1 prime and XA1 prime. So there are 2 liquid vapor states at P1 and T1. So the state is not fixed, so even though I have exhausted 2 degrees, because the phase rule says 2 degrees of freedom, then the state is automatically fixed. So I have chosen pressure and temperature, but the state is not fixed because I see one set of liquid vapor in coexistence. There is another also because the constant temperature line intersects the envelope at actually 4 points. That means 2 distinct vapor liquid states are there. So you cannot say the phase rule, you have to be interpreted very carefully, because when you just count the number of equations and unknowns, you need not always get a clear-cut answer, because you might have seen from even for the linear equations, the number of equations equals the number of unknowns. That is the whole idea of the degree of freedom. When you say there is a unique state, once you have chosen the degree of freedom, which means that initially I have, let's write the equations here. So what are the equations? One would be equal chemical potential of A, right, which is a function of XA, and mu B. Now the second equation, so 4 variables have already arrived: temperature, pressure, and the mole fraction in the liquid and vapor phase. Similarly, the equation two equations, 4 variables. So if I choose 2 variables, when I say the state is uniquely determined, on what basis do I say that? I say there are as many equations as there are unknowns. So it should give a unique solution. But we know that that need not really be the case, and this is a classic example. So all it says is that if I now fix the temperature at T1 and temperature at T1, now I have, this is YA. So I have fixed the temperature and pressure. These are 2 equations in XA and YA. Right? These are non-linear equations in general, so why should I expect it will have a unique solution? Classic examples are seen where I'm having multiple solutions for XA and YA. One solution is given by this, another solution is given by this. So we cannot really weigh the phase rule. It is our limited interpretation of the phase rule. So it says that the moment the degree of freedom is satisfied or chosen, the system of equations should yield a unique solution. There is no guarantee for that. Even for linear equations, you know, just because the number of equations equals the number of unknowns, the rank of the matrix is not full, you will not have unique solutions. It should come as no surprise at all. Right? We have to sort of state the phase rule more strictly. So what I also want to point out, on the other hand, I call this XA1. Suppose my choice is now P equal to P1 and XA equal to XA1. I am still choosing 2 variables. Degree of freedom is 2. Suppose I make this choice. Now, how is the state uniquely fixed or not? Maybe the diagram is not very clear because there are so many lines. So all I am saying is the pressure is fixed, 1 degree of freedom exhausted. Now XA1 I am choosing it to be this. Is the system fixed or not? No. Why not? There are no two. There is only one temperature. I have fixed XA to be XA1. Temperature is determined. YA is determined. There is only one state. No, it cannot be because this is what the diagram says. I fix XA. I fix the pressure. I fix XA. The liquid, that is the liquid. I can XA is not here. It is a two-phase liquid vapor. So is the temperature fixed or not? It is fixed. So what it means now is P1 is there, XA1, temperature is not known. Right? P1 is there, temperature is not known. XA1. Now I change same equations. I now change the specification. So I say I am giving you pressure equal to P1, XA equal to XA1. Clearly, you cannot have anything to do with this side. At XA1 there is only one temperature. At which liquid and vapor for the mole fraction of liquid being XA1 and pressure P1, there can be only one temperature. These don't come into play here. We are not specifying the temperature, specifying XA1. So I am excluding this. I am excluding XA2 from the picture by specifying XA1. Clearly then, what this figure shows, there will be a unique solution, T equal to T1, YA equal to YA1. Again, this should not come as a surprise, because I have not changed the specification. There are two entirely different, they are the same equations, but now in terms of two different sets of variables. Because earlier, the variables were mole fraction, XA and YA. Now the variables to be determined are temperature and YA. So it can have a different solution structure, because if you look at this whole problem in terms of this algebraic equations, nonlinear equations, there are 4 variables, and I have a choice. I have to choose 2. How many ways you can choose? 2 variables from 4 variables. 4 ways, or 4C2, 6 ways. I can in fact write down each of the, one can be temperature pressure, one can be temperature XA, one can be temperature YE. Right? And then what? Another can be pressure XA, pressure YE, another can be XA YE. So even though the basic equations remain the same, for each one of these specifications, the equation, you cannot expect the solution structure to be the same. So what it clearly shows is that for temperature and pressure I am getting multiple solutions for the mole fraction, but for pressure and mole fraction of A, I am getting a unique solution. Again, that should not come as any surprise, because the equations are different now. Now we are having equations in temperature and YA. Earlier, it was an equation in XA and YA, right? Derived from the same basic equation, but for each set, the equations that we have to solve are clearly different. Right? They are completely different set of equations. They are derived from the basic source. But actually, the equation, once you have to solve for T1 and XA means, another you have to solve for P and YA. The equations will obviously be different, because what you fix determines actual equation that you are going to solve. Right? All the 6 sets of equations can be obtained from the basic set, but each one, each specification they will be different, and clearly the nature of specification determines whether you have a unique or a multiple solution. So again, we cannot say anything just based on arbitrary 2 variables. You select everything will be fixed. It also depends on which 2 variables. So I think what the phase rule effectively says is that at least one set of two variables will be there from among the here 6 choices that will uniquely fix the state. That is all probably we can say. But we cannot say every set of two variables will uniquely fix the state. So azeotrope gives an example where you might have to modify some of the very drastic statements made in some books about what the phase rule really says, and then you cannot blame the phase rule for having failed in that case. Because all the time we are looking at systems of equations and unknowns to be determined, and the solution, because these are all generally non-linear equations, there is no question, no guarantee of uniqueness. It's surprising that in most of the cases you are getting unique solutions, right? You should not be surprised that the uniqueness fails, and the azeotrope has attracted a lot of interest because of this implication of the phase rule and what it means for specifying the state of the system. Are there any questions?
What is the reason certain compounds form azeotropes? What is the reason certain compounds form azeotropes in a thermodynamic aspect? What is the reason?
No, it is often associated. Why you have an azeotrope? Right? You are asking. Well, we give an explanation there in paper. It is usually correlated with the non-ideality of the mixture, especially the liquid mixture. Right? That is what leads to. We haven't said the ideal solution we have introduced. So, ideal solution will never show an azeotrope. If you model the liquid mixture as an ideal solution, it will never show an azeotrope. But what he says is that what is called as two different types of deviation from the ideal solution. One is called as positive deviation, another is negative deviation. So what Ravi says is that for sufficiently pronounced positive deviations from ideality, which can be related to the sign, the activity coefficient being greater than or less than 1, right? So the activity coefficients are greater than 1, that is called positive deviation from ideality. Positive deviation, he says, invariably leads to a minimum boiling azeotrope, a negative deviation leads to a maximum boil. But it doesn't mean that just because there is deviation from ideality, it will show an azeotrope, right? But certainly accounting for a deviation from ideality becomes essential when you have a system exhibiting an azeotrope. So from that point, it's a challenge for any model that will model the liquid phase, what model you choose. Clearly, ideal solution is ruled out if you have any idea that the system will show an azeotrope. So you have to take into account the deviation from ideality. Any other question? We will take that up. That's the first step we will take. Now we will start with the Ravi's law. It basically assumes ideal gas mixture and effectively ideal solution, and see how to carry out these calculations, which we haven't seen in detail. We will take that up in starting from tomorrow's class. So we will wind up for today. We meet again tomorrow and continue with the calculational aspects now of the phase.